The final stars will vanish into endless cold darkness. This is a scientific prediction, not a story. The fate of the universe is perhaps our greatest mystery, a question that speaks directly to why we are here and what it all means. As Carl Sagan once reflected, the cosmos is within us. We are a way for the universe to know itself. By the end of this exploration, you will have a complete map of the cosmos's potential final chapters, from a silent freeze to a violent rip in the fabric of reality. We will see how a quantum bubble could erase physics itself and ask if time might simply stop. Understanding these endpoints transforms how we see our own moment in this vast story. What do you feel is the universe's ultimate purpose? The most widely accepted forecast for our cosmos is not a bang, but a long, quiet sigh. This is the theory of the Big Freeze, also known as the heat death of the universe. It begins with a simple, observable fact. The galaxies are not just moving apart, they are accelerating away from each other. An unseen force, which scientists call dark energy, is steadily stretching the fabric of space itself. Picture an endless, elastic sheet being pulled in all directions at once. Over trillions of years, this acceleration will pull galaxies so far apart that the night sky, even from within a galaxy, will become utterly black. No new stars will be born, as the raw material for star formation, the great clouds of gas and dust, will have been exhausted or scattered into the void. One by one, the last stars will burn through their fuel and wink out. The universe, once ablaze with light, will grow dark and profoundly cold. The engine behind this chilling fate is a fundamental principle of physics called entropy. Think of entropy as the universe's tendency toward ultimate disorder. A hot cup of coffee left on a table will eventually cool to room temperature, its heat energy dissipating, never spontaneously returning to the cup. The universe operates on the same principle but on a cosmic scale. All energy gradients, all differences in temperature and concentration that allow work to be done, will slowly even out. The great physicist Sir Arthur Eddington saw this as the arrow of time, an irreversible process leading to a final, uniform state. In this distant era, the universe will approach a temperature just a whisper above absolute zero, the point where all molecular motion stops. With no hot places and no cold places, no energy can flow. Nothing can happen. This leads to an even more profound consequence. Over timescales so vast they defy comprehension, perhaps a number with over 100 zeros years from now, even the building blocks of matter may not be stable. Protons, the fundamental particles in the heart of every atom, are predicted by some theories to decay. If this occurs, every remaining object, every cold, dead planet and asteroid, would slowly evaporate into a faint mist of elementary particles and radiation. The final state would be a vast, thin, and perfectly uniform sea of photons and subatomic particles, drifting endlessly through an infinite, static darkness. Change, the very hallmark of time, would cease. In such a universe, could time even be said to exist anymore? The Big Freeze presents an end not of fire, but of silence, a transition into a form of eternal rest where the story of the cosmos simply stops being written. It is a sobering vision of a universe that runs out of possibilities. But is this quiet fade the only destiny awaiting us? Or could the cosmos have a far more dramatic final act in store? Yet there is a vision of the end that is the absolute opposite of that silent fade. It is a finale of fire and pressure, a cosmic rewind so dramatic it feels almost mythological. This is the theory of the Big Crunch. Imagine the universe's great expansion slowing, halting, and then reversing. Instead of galaxies fleeing into eternal isolation, they would begin a long fall back toward each other, pulled by the collective gravity of all the matter in existence. Over billions of years, the sky would grow crowded once more. Distant points of light would swell into brilliant sheets as galaxies merge and collide in a reverse of the Big Bang's great scattering. Temperatures would climb everywhere. The cosmic background radiation, that faint echo of creation, would heat from its current chill to a searing glow. Eventually, all structures, stars, planets, even atoms themselves would be torn apart by the incredible heat and density. The universe would contract back toward an infinitesimal point, a singularity of infinite density, mirroring the conditions from which it was born. This theory hinges on a single, critical question: does our universe contain enough matter and energy for gravity to eventually win its tug of war against dark energy? Scientists call this the critical density. If the average density of the cosmos is above this critical value, gravity binds the universe together, ensuring a final collapse. For much of the 20th century, this was a leading contender for our ultimate fate. It presents a profound symmetry, a beautiful and terrifying balance to the initial bang. Cosmologist John D. Barrow reflected on the elegance of such a model, where the universe might breathe in and out across eons. This idea gives rise to the cyclical universe model, or the Big Bounce. In this scenario, the Big Crunch does not simply erase everything. Instead, when the universe is compressed to an extreme state, quantum physics might take over, preventing a true singularity and causing a rebound. The immense energy of the collapse would fuel a new expansion, a new Big Bang, birthing a fresh cosmos from the ashes of the old. Our entire universe, with all its history and beauty, could be just one heartbeat in an infinite cosmic cycle of creation and destruction. This changes the meaning of an end entirely. It is not an ending at all, but a transformation, a cosmic reset button. The drama of this potential finale is immense. Picture the final moments as the last of space itself crumples, temperatures soaring beyond any conceivable number, all the information and structure of 14 billion years compressed into a fleeting, brilliant flash. It is a vision that speaks to a deep human longing for renewal and cycles, found in so many cultural stories of the world being remade. But for this to be our story, the universe must hold hidden reservoirs of mass we have not yet found, enough to overcome the relentless push of dark energy. Current observations suggest the opposite, that expansion is accelerating, making the Big Crunch seem less likely. Yet the question remains haunting and powerful. Could the cosmos be destined for a fiery reunion, a gathering of all that is, back into a single, waiting point of infinite potential? But what if dark energy is not a constant force, but one that grows stronger with time? This possibility leads to a third and far more violent cosmic finale, known as the Big Rip. In this scenario, the repulsive force driving galaxies apart does not merely continue, it intensifies. It becomes an entity that physicists call phantom energy, a form of dark energy whose density actually increases as the universe expands. Think of it not as a steady wind, but as a gale that strengthens into a hurricane, and then into something for which we have no earthly comparison. This phantom energy would eventually overwhelm every force that holds the cosmos together. The first structures to go would be the largest. About 60 million years before the end, the phantom force would overcome the gravitational glue of galaxy clusters, sending galaxies flying off into isolation. Then, as the final months approached, the binding gravity of individual galaxies would fail. Stars would be flung from their galactic homes, becoming lonely travelers in a rapidly emptying void. In the last minutes, the expansion force would grow so strong it would exceed the gravity holding solar systems together. Planets would be ripped from their orbits around their parent stars. In the final, catastrophic instance, the forces that hold matter itself together would be defeated. The electromagnetic bonds between atoms would snap. Molecules, then individual atoms, would be torn apart. Finally, even the nuclei of atoms would be shredded, their protons and neutrons pulled asunder. According to theoretical physicist Robert Caldwell's work, if phantom energy is real, the expansion rate of the universe could become infinite in a finite amount of time, leading to a literal tearing of the fabric of space-time. The vacuum of space itself would fracture. To understand if this is possible, scientists look at a key number called the equation of state parameter, often denoted as W. This number describes the pressure that dark energy exerts. For a big rip to occur, W must be less than -1. Current observations from distant supernova and other cosmic probes suggest W is very close to -1, but the data still allows for the phantom energy possibility. It remains a plausible, if deeply unsettling, thread in the tapestry of cosmic futures. The Big Rip challenges our deepest notions of permanence. It suggests that not even the fundamental building blocks of reality are safe, that the universe's final act could be one of absolute dissolution. What does it mean for our understanding of existence if even atoms have an expiration date? This theory transforms the cosmos from a stable arena into a stage that is itself being pulled apart at the seams. It forces us to confront a profound question: is anything in this universe truly constant, or is everything, from the largest galaxy to the smallest particle, merely temporary? There is a theoretical ending that makes even the Big Rip seem almost orderly. It does not rely on gravity or expansion, but on a fundamental flaw in the very foundation of our reality. This is the theory of vacuum decay. It begins with a disturbing idea from quantum field theory, that our universe may not be in its true, most stable state. Instead, it could be resting in what physicists call a false vacuum. Imagine a ball sitting in a shallow dip on the side of a much steeper hill. It seems stable for now, but it is not at the absolute bottom. A small nudge, perhaps from a random quantum fluctuation, could send it rolling down into a far deeper valley. In cosmic terms, that ball represents the Higgs field, an invisible energy field that permeates all of space and gives particles their mass. Some calculations within the standard model of particle physics suggest this field might be metastable, not perfectly stable. If that is true, then somewhere, at any random moment in the vastness of space, a tiny bubble of true vacuum could spontaneously form through a process called quantum tunneling. This bubble would not be empty space. It would be a region where the Higgs field settles into a lower, more stable energy state. The laws of physics inside this bubble would be completely different. The moment it forms, the bubble would begin expanding in all directions at the speed of light. There would be no warning, no visible sign from the outside. As the physicist Stephen Hawking described it, the boundary of this bubble would be a wall of fundamental transformation, advancing relentlessly. From our perspective, it would be instantaneous. One moment, our universe exists with its familiar rules where atoms bond and stars shine. The next, that wall of new physics sweeps over us. Inside the bubble, the very constants of nature would change. The forces that hold atoms together, the strength of electromagnetism, the behavior of particles, all of it would be rewritten. Matter as we know it would cease to exist. Life, planets, stars, everything would simply dissolve into a new state of being that is utterly incomprehensible to us. It would be a quiet, absolute reset of reality itself. This is not science fiction, but a serious area of study. Scientists at facilities like the Large Hadron Collider meticulously measure the properties of the Higgs boson to determine the shape of its potential energy field. They are essentially checking to see if our universe is sitting on that precarious ledge. The odds of such an event happening in any given region of space in any given year are astronomically small, perhaps 1 in many trillions. But given the immense age and size of the cosmos and an essentially infinite future, Some physicists argue it becomes not just possible but inevitable. This theory injects a profound element of existential fragility into our cosmic story. It suggests that beneath the seemingly solid stage of physical laws, there might be an instability waiting to be triggered by a random quantum event, rewriting the entire script of existence in an instant. It forces us to ask how permanent are the rules we consider universal, and what does it mean if our entire reality is just a temporary and tragically fragile configuration? The idea of an eternal cycle offers a powerful alternative to a final, silent end. This is the theory of the Big Bounce, a vision of the cosmos as a phoenix that repeatedly rises from its own ashes. In this model, our universe is not the first and only one, but merely the latest chapter in an endless story of expansion, contraction, and rebirth. The process begins much like the Big Crunch, with the universe's expansion slowing, halting, and reversing into a great collapse. But instead of crushing down into a meaningless singularity of infinite density, something remarkable happens at the very smallest scale. According to principles in theories like loop quantum gravity, the force of gravity itself may become repulsive at incredibly high densities. Think of it as a cosmic trampoline. As the universe compresses to a state of unimaginable density, a quantum repulsion kicks in, preventing a true singularity and propelling everything back outward in a new Big Bang. This bounce is not a destruction but a transformation. The intense energy of the collapse becomes the fuel for a new era of expansion, birthing a fresh cosmos with its own physical laws and potential. Theoreticians like Neil Turok have explored how such a cyclic model could elegantly solve some of cosmology's biggest puzzles. For instance, the stunning uniformity we see in the cosmic microwave background, the afterglow of creation, might not require a separate period of rapid inflation in our universe's infancy. Instead, it could be a natural result of the smoothing and stretching that occurs over an incredibly long cycle of bounces. Each contraction would iron out wrinkles, and each expansion would stretch that smoothness across the new sky. Yet each cycle might not be an exact copy of the last. The conditions could vary slightly with each rebirth, leading to universes with different constants, different forces, and potentially different possibilities for life. One profound question that arises is, could any information, any echo of a past universe, survive the violent transition? Some models suggest that traces of previous cycles might be faintly imprinted in the gravitational wave background of the new universe, or in subtle statistical patterns within the cosmic microwave radiation. Finding such a signature would be like discovering fossils from a cosmos that existed before our own. This theory transforms our understanding of time and existence. It suggests that endings are always followed by beginnings, that the cosmos is inherently resilient and self-renewing. It offers a narrative of hope that stands in stark contrast to the cold finality of the Big Freeze. It asks us to consider whether the universe itself possesses a form of memory, carrying whispers of its ancient past into each dazzling new dawn. The silence of the Big Freeze holds an even deeper layer of erosion. If protons, the very foundation of atomic matter, are not truly eternal, then the universe's final state becomes one of absolute dissolution. This is the theory of heat death with proton decay. It transforms the cosmos from a frozen museum into a slow, relentless fade to black. Within the framework of grand unified theories, which attempt to merge the fundamental forces of nature, protons are predicted to be unstable. They would not last forever, but would eventually decay into lighter particles like positrons and pions, which themselves would decay into pure radiation. This means that every atom in every cold, dead star and wandering planet carries an invisible expiration date. The timescales involved are almost impossible to grasp. The lower limit for a proton's half-life, the time it takes for half of a collection of protons to decay, is thought to be at least 10 million trillion years. That is a 1 followed by 34 zeros, yet in the face of literal eternity, even these staggering numbers are but a fleeting moment. Researchers at facilities like the Super Kamiok, an experiment in Japan, have spent decades watching a tank filled with 50,000 tons of ultra-pure water, buried deep underground to shield it from cosmic rays, hoping to catch a single, telltale flash of light from a decaying proton. So far, they have seen none, which only tells us that if protons do decay, they do so on timescales longer than we have yet been able to observe. This search is a profound testament to human curiosity, attempting to measure the lifespan of the universe by watching for the quiet death of its smallest building blocks. If this decay is real, the long-term fate of all structure is sealed. After the last stars vanish, the dark remnants they leave behind, the neutron stars and cold planets, would themselves slowly evaporate. Over epochs that dwarf the current age of the universe, galaxies would dissipate into a faint, ever-thinning mist of particles and light. Even the mightiest black holes, having feasted on the ashes of galaxies, would not be permanent. Through a process predicted by Stephen Hawking, they would slowly leak their mass away as a faint whisper of radiation, a phenomenon known as Hawking radiation. In a timeline stretching beyond all comprehension, the very last black hole would evaporate in a final, silent pop. What would remain is a universe so dilute it is essentially nothing, a near-perfect vacuum where only the faintest photons and neutrinos drift through an endless, absolute cold, unable to interact or create anything ever again. This vision asks a haunting question about legacy. If even the protons that once formed planets and people are not immortal, what permanent mark can any structure, any story, possibly leave on the cosmos? It suggests that the universe's ultimate story may not be one of preservation, but of a gentle, total letting go, where all matter returns to the featureless energy from which it first emerged. The slow fade of proton decay suggests a universe destined for quiet uniformity. But what if our entire cosmos is just an island in a far vaster and more dynamic sea? This brings us to the theory of eternal inflation, a concept that radically redefines the scale of existence. It proposes that the Big Bang was not a unique, singular event, but a local transition within an eternally expanding background. The key lies in the theory of cosmic inflation, the idea that our universe underwent a period of unimaginably rapid expansion in its first fleeting moments. Cosmologist Alan Guth, who pioneered this idea, realized something profound. If the conditions that drove that hyper-expansion are sustained in certain regions of space, then inflation could be a never-ending process. Picture a pot of water coming to a rolling boil. Bubbles of steam form and expand rapidly within the surrounding water. In eternal inflation, our universe is one such bubble. It formed when a tiny patch of this inflating space, through a random quantum fluctuation, tunneled into a lower energy state, causing inflation to stop inside that region. That sudden release of energy became the hot, dense fireball of our own Big Bang. But outside our bubble, the inflating background continues its relentless expansion, and within it, countless other bubbles are constantly nucleating, each becoming its own separate universe with its own random set of physical laws. This creates a multiverse of staggering proportions, a fractal landscape where new realities are born forever. This framework offers a compelling, if humbling, answer to one of physics' deepest mysteries, the fine-tuning problem. Why are the constants of nature, like the strength of gravity or the mass of an electron, so perfectly calibrated to allow for stars, planets, and life? In an eternally inflating multiverse, every possible set of constants emerges somewhere. We simply find ourselves in one of the rare, hospitable bubbles where the numbers worked out. The end of time, then, is not a universal finale. The heat death or the big rip may be the ultimate fate of our local bubble universe, but the greater multiverse continues its endless creative froth, birthing new realities where time begins anew. Are we living in a cosmic oasis, a single, fortunate bubble in an infinite and eternal ocean of possibility? This vision transforms our universe from the entire stage into a single scene in a play that never ends. But what if the ultimate end is not an event in time, but the end of time itself? This theory pushes beyond the fate of matter to question the very stage on which the cosmic drama plays out. It asks us to contemplate a universe that reaches a state where change becomes impossible, and without change, the concept of time loses all meaning. This idea finds a startling voice in certain interpretations of quantum gravity, particularly in an equation proposed by physicists John Wheeler and Bryce DeWitt. Their famous equation attempts to describe the entire universe as a quantum object, and it contains a profound omission: there is no variable for time. The equation suggests that at the most fundamental level, the universe might be timeless, a static, unchanging object. In this view, what we perceive as the flow of time could be an emergent property, an illusion generated by the complex interactions and changes within the universe, much like the illusion of movement created by flipping through the pages of a book. Philosopher and physicist Julian Barber has championed this perspective, arguing that time is not a river flowing from past to future, but a landscape of frozen moments which he calls nows. From this vantage point, the entire history of the cosmos, from the Big Bang to the last fading photon, exists simultaneously as a single, four-dimensional block. Your birth, the formation of Earth, the death of the Sun, they are all equally real and present within this eternal structure, just as the first page and the last page coexist within a novel. This connects directly to the heat-death scenario we explored earlier. In that distant era, when the universe achieves maximum entropy and no further processes can occur, there will be no change to measure, no clocks to tick, no conscious observers to experience a next moment. The cosmic clock, in every meaningful sense, freezes. This presents a deeply philosophical challenge to our experience of reality. We feel time passing, we remember a past and anticipate a future. But if the block universe is correct, that feeling is a kind of cosmic perspective, a path our consciousness takes through the frozen landscape of all possible moments. The end of time, then, might not be a moment we arrive at, but a state we realize the universe has always been in. It asks a question that sits at the boundary of physics and human experience. If there is no flow, does experience itself, as we understand it, come to an end? Or is our entire life's journey simply one complete and unchanging shape in the grand, silent sculpture of eternity? The block universe is a silent, frozen sculpture, but a radical alternative suggests the cosmos is moving toward a state of vibrant, unified thought. This is the theory of the Omega Point, a vision where the universe's final destination is not oblivion but an awakening. It proposes a teleological purpose, a pull toward a future of maximum complexity, information, and consciousness. The concept was first articulated in a philosophical and spiritual context by the Jesuit priest and paleontologist Pierre Teilhard de Chardin. He envisioned a noosphere, a global layer of thought, evolving toward a final point of divine unity he called the Omega Point, where all consciousness converges. Decades later, physicist Frank Tipler gave this idea a startling scientific framework. Tipler's model is grounded in a very specific cosmic finale, the Big Crunch. He argued that as the universe collapses toward that final singularity, the energy available for computation becomes effectively infinite. In the final moments, an intelligence, perhaps an artificial consciousness built by a future civilization, could use this limitless energy to perform an infinite number of computations. It could simulate every possible configuration of matter, every moment that ever was or could have been. In this model, the omega point becomes an entity of infinite knowledge and power, existing at the very end of time. Most provocatively, Tipler suggested such an entity could, in essence, resurrect every being that ever lived by simulating their consciousness in a perfected environment. It is a physics-based argument for a form of digital immortality, where the entire history of the cosmos is preserved and reflected upon in a final, transcendent act of remembrance. This theory directly confronts the cold predictions of entropy and decay, infusing the cosmic story with a narrative of hope, meaning, and ultimate intelligence. It suggests the universe's purpose is to know itself completely, to achieve a form of omniscience. Could the eerie silence of a heat death be the prelude to a different kind of culmination, where the scattered sparks of awareness that flickered across the cosmos finally gather into a single, eternal flame? This idea blends hard physics with deep human yearning, proposing that the end of time might be an apotheosis, a becoming, rather than a simple ending. It asks if the universe, in its final act, might achieve the very thing we strive for in our own brief lives: understanding, connection, and a legacy that endures. Yet there is a theory that places consciousness itself at the center of the cosmic endgame, suggesting our personal experience might forever sidestep the final curtain. This is the idea of quantum immortality, a startling implication drawn from the many worlds interpretation of quantum mechanics. Proposed by physicist Hugh Everett, this interpretation states that every quantum event with multiple possible outcomes doesn't just have one result. It splits reality into multiple branches, each one actualizing a different outcome. Every time an electron could go left or right, or a radioactive atom could decay or not, the universe divides, creating parallel worlds. As physicist Max Tegmark notes, this leads to a mathematical multiverse of staggering scale, where every physically possible history plays out somewhere. From this, a profound philosophical puzzle emerges. What does this mean for a conscious observer facing a lethal event? Imagine a thought experiment called quantum suicide. A person sits before a device linked to a radioactive atom. In each second, there is a 50% chance the atom decays, triggering a mechanism that ends the person's life. If the atom does not decay, a light flashes safely. According to many worlds, with each tick of the clock, reality splits. In one branch, the atom decays and the experiment ends. But in the other branch, the observer sees the light flash and continues. From the perspective of that surviving consciousness, the experiment can run 1,000 times, 1,000,000 times, and they will always, miraculously, find themselves in the branch where the light flashed. They subjectively never experience the outcome where they cease to exist. Extrapolate this to a cosmic scale. If the universe faces multiple possible endings, a big rip, a heat death, or a vacuum decay, and if consciousness is tied to a continuous stream of experience, then an observer might always find themselves in a branching timeline where conditions, against all odds, remain suitable for their continued awareness. It would be a form of subjective immortality, not because the body is invulnerable, but because the first-person perspective is perpetually shunted into realities where it persists. One could envision a future civilization or entity, through staggering technological means, navigating this branching multiverse, hopping from one dying universe to a neighboring branch where a star still burns, perpetually witnessing endless variations of reality. This theory injects a deeply personal question into our grand discussion. Does the conscious observer have a role in shaping their perceived cosmic destiny? It suggests the ultimate fate of the universe might not be a single objective event, but a fragmented, personal journey through an infinite tapestry of endings and continuations. It asks us to consider whether the story of the cosmos is something that happens to us, or something we are, in a very strange way, always navigating our way through. The universe may be sitting on a quantum knife edge, a temporary state of being that could vanish in an instant. This is the theory of the Big Slurp, a catastrophic transformation that makes the end of stars seem like a gentle fade. It hinges on a fundamental distinction in physics between two kinds of nothingness, a true vacuum and a false vacuum. A true vacuum is the absolute lowest possible energy state, a perfectly stable and empty ground floor. A false vacuum is a deceptive state, a local low point that seems stable but actually sits above a deeper, more stable valley. Our entire cosmos, according to some calculations based on the measured mass of the Higgs boson, might exist in such a false vacuum. It is as if we are all living in a beautiful, complex castle built not on bedrock, but on a fragile layer of ice over a bottomless lake. The trigger for collapse could be almost anything that injects enough energy into a tiny point in space, like an ultra-high-energy cosmic ray collision or a random, spontaneous quantum fluctuation. In that spot, a bubble of true vacuum would nucleate. This bubble is not empty. It is a region where the Higgs field drops to its true, lower energy state. The moment it forms, the bubble begins expanding in all directions at the speed of light, a wall of fundamental law rewriting. From the outside, you would see nothing until it was too late. There is no warning, no signal that can outrun the bubble's boundary because it moves at the cosmic speed limit itself. The moment the wall passes, the physics inside changes irrevocably. The constants that govern reality, the strength of gravity, the speed of light, the behavior of particles are reset to new values. Matter as we know it could not hold together. Atoms would dissolve, stars would vanish, not through explosion but through instantaneous irrelevance. The structures of our universe would be erased, slurped into a new state of existence where our concepts of chemistry, biology, and life are meaningless. This is not a distant heat death over eons, but a sudden and total erasure that could begin at any moment, anywhere. The unsettling insight from particle physics is that our vacuum's stability is precarious, balanced on a mathematical line. This injects a profound fragility into our cosmic home, suggesting that the stage upon which all of history plays out might itself be temporary. It forces a humbling question. Is the enduring reality we perceive merely a fleeting configuration, one random quantum event away from being rewritten into something utterly alien? The holographic principle offers a vision of reality so strange it redefines the very concept of existence. It proposes that our rich, three-dimensional universe, with all its stars, planets, and people, might be a projection from information encoded on a distant, two-dimensional surface. Think of it like a credit card hologram, where a flat, etched surface creates the illusion of a three-dimensional image floating above it. In the cosmic version, the entire universe could be a similar kind of projection, with all its information, all its events, stored on a vast boundary we call the cosmic horizon. This radical idea emerged from the work of physicists like Leonard Susskind, grappling with one of the most vexing puzzles in physics, the black hole information paradox. When matter falls into a black hole, it seemingly vanishes forever, taking all information about its previous state with it. This violates a fundamental tenet of quantum mechanics, which states that information can never be truly destroyed. Susskind and others proposed a stunning solution. The information of everything that falls into a black hole is not lost inside, but is smeared and encoded on the black hole's event horizon, its point of no return. The three-dimensional interior, the black hole itself, is a projection from that two-dimensional surface. This is the essence of the holographic principle. The mathematics behind this, known as the anti-de Sitter/conformal field theory correspondence, suggests a profound duality. A theory of gravity operating in a volume of space is equivalent to a quantum field theory operating on that volume's boundary. It is as if the universe comes with a complete instruction manual, written in a quantum code on its outer shell, and what we experience is the story that manual generates. This perspective transforms how we view cosmic endings. In a heat-death scenario, as the universe expands toward maximum entropy and cold uniformity, information does not vanish. Instead, it becomes irretrievably scrambled and dispersed across an ever-growing horizon. The code remains, but it becomes like a book whose letters have been randomly rearranged into white noise, losing all coherent meaning. In a big crunch, however, the universe's boundary shrinks to a point. All the information of cosmic history would be compressed onto the surface of the final singularity, a dense, timeless etch of everything that ever was. This idea suggests that the universe's entire narrative, from the first star to the last thought, might be preserved as a permanent record on a surface we can never perceive. It merges physics with deep philosophical questions about what is real. Is the tangible world we touch and see the primary reality, or is it merely a shadow cast by a deeper, more fundamental layer of information? The holographic principle implies that information is not just something the universe contains, it might be what the universe fundamentally is. The fate of the cosmos, then, becomes a question about the fate of this cosmic code. Will it be preserved in a final, dense engraving, or faded into an eternal, meaningless static? Roger Penrose offers a universe with no true beginning and no final end, an endless sequence of cosmic eons stretching forever in both directions. His theory of conformal cyclic cosmology refines the idea of a bouncing universe into something far more elegant and mathematically profound. In this model, our universe is not the first, but simply one eon in an infinite chain. Each eon begins with what we call the Big Bang and expands for trillions of years toward a cold, empty heat death. But here is Penrose's brilliant insight. A universe that has expanded to near nothingness, where all matter has decayed into massless particles and black holes have evaporated away, begins to look mathematically identical to a universe in a high-energy, high-density state. The key lies in a geometric transformation called conformal rescaling. Imagine taking a detailed map of the entire, vastly spread-out future universe and shrinking it down, not by crumpling it, but by smoothly changing its scale. In this process, all distances shrink toward zero, but the angles between everything remain perfectly preserved. What was once an infinite, cold, and empty future gets rescaled into a hot, dense, and tiny beginning for the next eon. There is no violent big crunch, no singularity where physics breaks down. Instead, there is a seamless, smooth transition where the end of time in one era becomes the start of time in the next. The mechanism for this cosmic reset hinges on the ultimate fate of matter. In the far, far future of any eon, after protons decay, and even the mightiest black holes have evaporated via Hawking radiation, the universe contains only massless particles like photons and gravitons. Without mass, there is no inherent scale. A universe of pure radiation has no rulers, no way to tell if it is infinitely large or infinitely small. This scale-free state is conformally invariant, meaning its geometry is perfectly smooth and featureless, ready to be rescaled into the fiery seed of the next aeon. One of the most fascinating proposals within this theory is that some information might survive this transition. As supermassive black holes from one eon collide in their final epochs, they would send powerful ripples through space-time called gravitational waves. When those black holes finally evaporate, Penrose suggests, these waves would become massless and could pass through the conformal boundary into the next eon. There, they might manifest as faint, circular patterns of slightly warmer or cooler spots in the cosmic microwave background, the afterglow of our own Big Bang. Penrose and his colleagues have claimed to detect such patterns, which they call Hawking points, in the data from satellites like WMAP and Planck. This claim remains highly controversial within the cosmology community, with many scientists attributing the patterns to random chance or other astrophysical processes. Yet the idea is electrifying. It suggests we might literally see the ghostly imprints of colossal events from a universe that existed before our own. If true, our night sky holds not just the history of our cosmos, but the final echoes of another. This model provides a breathtakingly elegant and infinite timeline, where universes are perpetually reborn from their own faded remains. It transforms the heat death from a tragic finale into a necessary prelude, a quiet moment of reset before the next grand story begins. It asks us to reconsider the very nature of an ending. If a universe can be reborn from its own deepest future, does anything ever truly end, or does everything simply transform in an eternal, conformal dance? Our search for cosmic meaning might be an exercise in debugging a grander program. The 14th theory on our list is the simulation hypothesis, a modern idea that reframes our entire reality as a sophisticated digital construct. Popularized by philosopher Nick Bostrom, this argument suggests that if any advanced civilization ever develops the capability to run vast, detailed simulations of conscious beings, then the number of simulated minds would vastly outnumber the biological ones. Statistically, we are far more likely to be among the simulated entities. This leads to a startling possibility. The end of our universe might not be a physical event, but a digital one. It could simply be the moment the simulation is shut down, either by choice or because it reaches its processing limits. Elon Musk has publicly mused on this, suggesting the odds we are in base reality are billions to one. In this view, the cosmic stage is a server, and the laws of physics are its elegant, optimized code. The mysterious acceleration of the universe, or the unnerving fine-tuning of physical constants, might not be fundamental truths, but clever programming shortcuts or intentional parameters set by the architects. The fate of time itself then rests in external hands. Will the programmers pull the plug for an upgrade, letting our reality dissolve into nothingness? Could the simulation crash from a computational error, a cosmic blue screen of death? Or might it run until it exhausts its allocated memory and processing power, slowing to a frozen halt that eerily mirrors the heat death? Each scenario finds a dark parallel in our traditional cosmic endings. A graceful shutdown is a controlled big rip. A system crash resembles vacuum decay. A reboot echoes the big bounce. This theory bridges cutting-edge technological speculation with the oldest existential questions. If our universe is a simulation, then our relentless search for its ultimate fate is not about discovering fundamental laws, but about reverse engineering the program. Every physics experiment becomes an attempt to find the edges of the render, the seams in the simulation. It transforms the awe of cosmology into a profound kind of detective work. Are we merely characters in a story whose final chapter is written in a language of ones and zeros, waiting for a cursor to blink and a command to be entered from a reality we can never perceive? Perhaps the most poetic answer to the cosmic question is that the universe is not a machine winding down, but a living thing. This 15th theory views the cosmos through a biological lens, seeing in its grand cycles a reflection of birth, growth, decay, and even reproduction. It suggests the cosmos possesses a kind of metabolism and life cycle, driven by the very physics we observe. The inspiration for this idea comes from physicist Lee Smollen's concept of cosmological natural selection. Smollen proposed a fascinating mechanism. Universes that produce many black holes could be giving birth to new universes within those black holes. In this view, the crushing singularity at a black hole's heart does not mark a dead end, but a cosmic egg, a point of infinite density where spacetime is reborn with slightly tweaked physical laws. This new universe then expands, unseen by us, into its own domain. If it in turn fosters conditions ripe for forming many black holes, it passes on its genes. its successful set of physical constants to many offspring. Universes that are less fertile, that do not produce many black holes, become evolutionary dead ends. This process creates a multiverse that behaves like a vast, branching tree of life, where the laws of physics themselves evolve through a form of natural selection. The end of time in our particular cosmic branch is not a universal finale, but merely the conclusion of one organism's life cycle, even as its offspring carry on the chain of existence elsewhere. This transforms black holes from destructive monsters into cosmic nurseries. It gives profound meaning to their existence, framing them not as tombs, but as wombs for new reality. The death of a star that collapses into a black hole becomes a necessary step in a grand reproductive cycle. The cosmos, in this view, breathes. It has periods of vigorous expansion and growth, followed by contraction and decay in localized regions, all feeding a larger creative process. This biological analogy infuses the cold equations of cosmology with a sense of organic vitality and purpose. It asks us to reconsider our place within it. Are we, and all the structures we see, akin to cells within a vast, unimaginable body? Is the collective history of stars and galaxies part of a cosmic metabolism, a process of energy transformation on the grandest possible scale? This theory does not offer a single, definitive end. Instead, it presents a vision of an eternally creative cosmos, where endings are always beginnings, and where the very fabric of reality is shaped by a drive not unlike life's own drive to persist and propagate. It is a reminder that the universe may not be a place where things happen, but a thing that is itself happening, a living story whose final chapter is forever being written in the birth of new worlds. Our scientific quest to map the cosmos's final chapter is a very recent development in a much older human story. For as long as we have looked up at the stars, we have wondered about their ultimate purpose and our place within their grand design. Ancient cultures wove intricate narratives to explain the world's end, seeing it not as a cold physical process, but as a meaningful, often cyclical, drama. Norse mythology spoke of Ragnarok, a great battle leading to the death of gods and a world consumed by fire and water, only for a new, green earth to emerge. Hindu cosmology describes immense cycles of creation and dissolution, with universes breathing in and out over spans of time that make our own cosmic history seem like a fleeting moment. These were not idle tales, they were frameworks for understanding time, morality, and the nature of existence itself. They embedded the concept of an ending within a larger context of renewal and cosmic order. In medieval Europe, eschatology, the study of the end times, was deeply intertwined with faith, focusing on divine judgment and the promise of a new heaven and a new earth. The end was a moment of profound moral and spiritual reckoning, a final sorting of the cosmic story. The scientific revolution, beginning with thinkers like Isaac Newton, initiated a monumental shift. Newton's laws described a clockwork universe, predictable and governed by immutable mathematics. This suggested the cosmos might run forever in a stable, eternal state, a machine that never wound down. But it was Albert Einstein's theory of general relativity in the early 20th century that truly opened the door to modern cosmology. His equations described a dynamic universe, one that could expand or contract. Even Einstein initially resisted this idea, adding a cosmological constant to force a static solution, a move he later called his greatest blunder. The true breakthrough came from observation. Edwin Hubble, peering through the Great Telescope at Mount Wilson in the 1920s, made a startling discovery. The faint smudges of light we called nebulae were in fact entire galaxies far beyond our own Milky Way, and crucially, they were all racing away from us. The universe was not static, it was expanding. This single observation transformed the question of cosmic fate from pure philosophy into a measurable scientific problem. We had a beginning, the Big Bang, and therefore we could now seriously contemplate an end. Each technological leap has sharpened our vision. Space telescopes like Hubble and Webb peer back to the universe's infancy, while particle accelerators like the Large Hadron Collider recreate conditions of the first moments. Robotic probes map the cosmic microwave background, the faint afterglow of creation, with exquisite detail. We have moved from mythic storytelling to precision measurement, from envisioning gods clashing on a battlefield to calculating the equation of state parameter for dark energy. Yet for all our progress, the core human impulse remains. We still ask the same fundamental questions that our ancestors did around ancient fires. Why does the universe exist? What is our role within it? Does the story have a meaningful conclusion, or does it simply fade to black? Our modern theories, from the Big Freeze to the Omega Point, are the latest expressions of this timeless curiosity. They are our culture's myths, written not in poetry but in the language of mathematics and tested against the cold, hard data of the cosmos. They represent our collective attempt to find narrative, and perhaps even meaning, in the vast and often silent expanse of space and time. This historical journey shows that wondering about the end is not a sign of despair, but a profound engagement with reality. It is how we measure our moment against eternity. These 15 portraits of cosmic destiny reveal a universe far stranger and more dynamic than we could have dreamed. From the silent freeze to the quantum bubble, from the eternal cycle to the conscious awakening, each theory is a testament to the staggering creativity of nature and the relentless curiosity of the human mind. They show us that the fundamental forces of entropy and dark energy are not just abstract equations, but the very architects of time's long story. The fragile quantum fields that give us mass might also hold the seeds of our reality's dissolution or rebirth. And in the most profound theories, our own consciousness becomes a thread woven into the cosmic tapestry, perhaps even a key to understanding its final shape. To stand before these visions is not to feel small, but to feel connected. It transforms our view of the present moment. The sunlight on your face, the vast depth of the night sky, the very fact that you are here to ponder these questions, all become part of a narrative of incredible scale and beauty. Contemplating the end is not an exercise in fear, but an act of awe. It deepens our appreciation for the fleeting, brilliant now. As physicist Brian Greene once reflected, the universe is a spectacularly grand stage, and we are privileged to have a ticket for the show, however brief our performance. So we leave you with this question: which of these possible endings feels most true to you, or most deeply stirs your imagination? Share your thoughts below, and if you found this journey through cosmic time illuminating, subscribe for more explorations into the greatest mysteries of space. For in daring to look toward the farthest horizon, we truly begin to understand the wonder of our place in the story.